Hello and welcome to Pharma-info with Shubhashish. Now today's topic is Beckmann rearrangement reaction, right? Now straightway we'll just dive into the main topic, right? So Beckmann rearrangement reaction, when your assignment is to convert a ketoxime or ketoxime, you want to convert a ketoxime into a, that need to be converted to a N-substituted amide, N-substituted amide. The underlying mechanism is Beckmann rearrangement reaction. So it was explained by the scientist, developed by the scientist Beckmann. Fine. So ketoxime N-substituted amide. First, let us see that what is oxime, right? Oxime is the one. So let's do one thing. From the name itself, we can get the information about a keto, right? So that means in the very process of making an oxime, right, it is the keto moiety that must participate, right? Okay. That must come into place, right? So when you are trying to convert a keto into an oxime means, see, so this is the keto moiety when it is interacting with a hydroxylamine, right? Hydroxylamine, that means H2NOH, right? Hydroxylamine. So what will happen? As I said keto, I should write R1, I should write R2, okay, it is something like this, fine. So what will happen? What is expected when they come close together? What is expected? There is an expulsion or removal of water, fine. So once the water leaves, okay, so what will happen? What is the resultant product? The resultant product is found to be like this, fine. So this is nothing but your ketoxime. So this is the feature of ketoxime. That means the hydroxyl is still attached to the nitrogen. Only thing is that earlier the nitrogen was also linked to the two hydrogen. This two hydrogen at the same time from the keto the oxygen, right? They they were united, right? And just leave the reaction reaction media, right? So what will happen as a result of it? What will happen? From both the fragments, okay, connection was built, and it was the connection that eventually gave rise to the formation of what? Formation of oxime. So this is ketoxime. Suppose you started with an aldoxime. What is aldoxime? Aldoxime means not with a keto, rather one of the R is found to be a hydrogen. When your starting material is not found to be a ketone, rather an aldehyde, so what will happen? The same reaction will proceed, okay? The same reaction will proceed, but the thing is that instead of ketoxime, you are going to get aldoxime. So when R1 equals to R1 and R2, both are not found to be hydrogen, so that time there is a formation of what? Ketoxime. But when R1 or R2, either of them is hydrogen, so that time your end product will be aldoxime. Fine. So this is basically the difference between ketoxime and aldoxime, right? Now back to business here. So it is the ketoxime. So ketoxime is clear. So this is found to be the feature of ketoxime. Fine. So this is your ketoxime, where R1 and R2, neither of them is found to be a hydrogen. Both are found to be either alkyl or aryl or some heterocycles, right? So that time we can call them as ketoxime. Fine. Chalo, now your goal is to get N-substituted amide. That means no longer the oxime is there. Fine. So the oxime. So suppose we have taken this as a starting material, this as a starting material, right? So what am I supposed to get once the reaction is over? I just want to convert this into R2 C double bond O NH R1. As I said, it's a rearrangement. It's not a substitution reaction, right? It's a rearrangement. That means everything should be there. Whatever components that basically constituted the primary or the initial reagent, right, or the starting material, right, in the final product also you'll find there is no nothing. That means the final product will not lose any component, right, which was there with the starting material. Fine. Only thing is that things got rearranged, and in the very process of rearrangement, what happened? The property got changed. Earlier it was oxime, right now it is an amide. Fine. So amide and oxime both are not behaving in a similar way, because amide is CONH and oxime is C double bond NOH. Fine. Chalo. So this conversion is expected. Fine. So this conversion is according to Beckmann rearrangement reaction. Now the thing is that how this conversion took place, right? That means in this very conversion, that means there are several reagents which are introduced, right? And the prime reagent seems to be an acidic substance, right? Now, what are the acidic substances that you can introduce here, right? Now, acidic substances, the options are, if I just write the options are found to be PPA, that is polyphosphoric acid. Okay, you can take fuming H2SO4 as well, right? Like SO3 H2SO4, fuming H2SO4, right? You can even take BF3, boron trifluoride, right? Then even you can take phosphorus pentoxide as well, P2O5, phosphorus pentoxide. So these are even PCl5, right? PCl5, phosphorus pentachloride as well, right? So these are found to be the options, right? So that means all are found to be concentrated one, whether it is a polyphosphoric acid, fuming H2SO4, then boron trifluoride, then your P2O phosphorus pentoxide, then phosphorus pentachloride, right? All are found to be a concentrated acid. So these are found to be the options. I am not telling these are the combinations that you are going to take all together, right? Either of them can be chosen, right? But the thing is that for each and every reagent which you are going to choose as an acid, right, make sure that the condition will differ, and definitely differ, right? Condition will definitely differ, right? Chalo. Now the thing is that, so what are the conditions now? Along with, and the condition is found to be either extreme temperature or below 0 degrees centigrade. Fine. So now let's do one thing. Let us see that as I said, as per the when you are opting for, say, in the very process of opting different acids and all, the conditions will differ, right? Now let us do one thing. Let us just see that what are the different conditions, or what are the different, see, in which case let us see the corresponding conditions, right, for each and every acids, right? Because this two will remain same. This is the starting material. This is found to be the amide. So this one is oxime, preferentially ketoxime, and this one is found to be N substituted amide, right? So now let's give you some examples, right, where what exactly we are going to do. Fine. Suppose your starting material is found to be ketoxime, right? This will remain same. Let us do one thing. Let me do one thing. Let me just write here ketoxime, right? Ketoxime, and ketoxime is getting converted to N substituted. As I said that it is the kind of H2, the kind of acid that you are taking, the condition will differ, right? Suppose you have opted what? PCl5. Then ether should be the media, right? Media for the reaction, right? Now that time the temperature must reach minus 20 degrees centigrade. This is all about here. When you are opting PCl5, make sure that the reaction should be extremely cold condition, minus 20 degrees centigrade. Fine. This need to be maintained. Fine. Suppose instead of PCl5, you have chosen what? You have chosen like your PPA, that is polyphosphoric acid, right? What will be the condition? If you are taking polyphosphoric acid instead of PCl5, that time the condition will be extremely high temperature. That means 95 degrees centigrade to 130 degrees centigrade. Fine. So this is found to be the conditions when you are opting PPA, not PCl5. Fine. Similarly, if we are going to take formic acid, suppose you are taking what? Formic acid. Fine. When we are choosing formic acid, like your HCOH, right? So that time simply refluxing, right? Simply refluxing. Okay, fine. So these are found to be the conditions, right? These are found to be the conditions which need to be maintained, right, while opting different acids. As I said, when your job is to convert ketoxime into N-substituted amide, right? These are the possible options that is there with you, right? These are there with you. Fine. So on the basis of the the acid which you are going to select, right, the condition will differ. So these are found to be the various conditions, right, involved in opting the acids and all. Fine. So this is all about here the one that we are going to do. That means the chemical reactions involved in Beckmann rearrangement reaction, right, and the prerequisites, or we can say the reagents which are used, right, apart from ketoxime, right. So now let's jump into the next level, that is next thing, that is your mechanism, right. Fine. So coming to the mechanism, right, because Beckmann rearrangement reaction, how the mechanism, or how it is being operated actually, mechanism. So reaction mechanism. Fine. So reaction mechanism, how it proceeds actually. Look, for our convenience, let's do one thing. Let me just write the ketoxime in this way, so that at least you can at least you can sense that yes, which is that departing moiety, right? And which is the departing moiety, or what are the moieties which are involved in the process of rearrangement, right? I'm not telling the entire component will get shuffled, right? The entire each and every elements will shuffle their positions, right? In that very process of rearrangement, only few components they are changing their relative positions and all, fine. So likewise, I'm just write here, okay, let me just write here R, fine. And here I am going to take W, because W is the one which is basically participating in the process of rearrangement, right? Assume that W is found to be an alkyl, right? It can be an heteroaryl, it can be an aryl as well, fine. So anything, right? Now this is for the convenience of presentation, fine. So as we have started with an oxime, right? So oxime is found to be like this. Let me just put the lone pair over here, and finally we have a hydroxyl, fine. Hydroxyl do have some lone pair, fine. Chalo. So now what is expected initially? So initially what will happen? So let me do one thing. WR equals to, they can be either alkyl, they can be aryl, they can be heteroaryl, anything, right? Heteroaryl, fine. Chalo. So initially let me just take the very lovable reagent or acid, that is your H2SO4, fine. Okay, fine. Let me do one thing, let me just put H2SO4. All I want to carry out the reaction in presence of H2SO4. So H2SO4 is found to be a proton donor, right? What is the purpose of proton? See, in that very process, this proton will basically protonate the hydroxyl. So initially what will happen, this proton supplied by H2SO4 will hydroxylate, will protonate what? This hydroxyl, right? So once that means this is the hydroxyl which is expecting what? A proton, right? Okay. So once the proton is attached to this particular location, so what will happen? The intermediate will acquire this kind of form, yes or no? Right? Fine. So what next? Ab kya hona hai? Now once this has been charged, so what will happen? Now it has developed the tendency to leave the compound. Because the oxygen has already taken a charge, right? No longer it will try to stay in the form of this, rather it will try to gain its default or the native state, right? So what will happen? This has grown a tendency to leave the compound, right? Now in the very process of leaving the compound, all the necessary arrangement we have made to protonate the oxygen, fine. So what will happen now? Will come. Now consider this as an alkyl group, fine. This is an alkyl group, right? Now this alkyl group is linked to the sp2 hybridized carbon, is connected to the sp2 hybridized carbon, right? Now as it is an alkyl group and this one is found to be the hydroxyl group which has already been protonated, right? Both are in anti-relationship. Because earlier it was hydroxyl, right? Earlier it was hydroxyl and this was methyl. Both are in anti-relationship, what we can say, fine. So now what will happen? Now as this condition, as it has acquired this kind of form, as a result of it, what will happen? Now this got the power to attack what? This nitrogen, fine. So as a result of it, what will happen? Once this will try to form a bond with this nitrogen, this will leave. Because if I just see or compare the electronegativity of this nitrogen and oxygen is found to be more electronegative, thus it will definitely pull the entire electronic cloud, which is basically involved in making this particular covalent bond, right, towards it, and thus leave the compound. It is expected, fine. So what will happen here? So once this has happened, right, what will happen? That means there is an elimination of water, expected elimination of water, fine. So as a result of it, what will happen? Since this will this attack this one, right, along with the this bond, right? So the entire cloud will come along with it, fine. So what will happen to this carbon? This carbon will acquire what? A positive charge, right? So let me just write it down, fine. So this will get the positive charge. We have a R over here. Then we have a nitrogen. Then now the thing is that, so for my convenience, let me do one thing. Let me just keep the W here. Keep the W here, fine. Keep the W here, fine. So now this is found to be the state which this acquired, right? Fine. What next? The next is a nucleophilic attack. Now since water has already left, right, now it can serve, now still it is in the media, right, or we can say in the reactor, fine. So what will happen? Now this can act as a nucleophile and we have an electron deficient center here. So now what next? The next is the electrophilic attack. The nucleophilic attack at electrophilic center. So this is found to be the electron deficient center, fine. Chalo. So now let's do one thing. Let us just place the water molecule here. Water molecule, by virtue of this lone pair, what will happen? This will try to form a bond. Right? This will try to form a bond, right? So what will happen? As this will try to form a bond, what will happen? This will get, this bond will be broken, right? Why? Because as the lone pair has been given to this carbon, what will happen? This will get the positive charge. To replenish the positive charge, this hydrogen has to leave, leaving the pair of electrons. Now this will replenish the deficiency, right? The transient deficiency, what we can say. Fine. Now, what next? So what happened here? Here, as water is serving as a nucleophile, so I am just putting here water like this, and in this very process, what will happen? This H will go off, right, to replenish the deficiency, right? So thus, can I write like this? Minus H plus? Yes, of course. Now, what next? Ab kya hona hai? Now, the thing is that, so what will happen here? RC, double bond N, this remains same, we have a W over here, now we have O and we have a hydrogen, fine. This is the one that is getting formed, right? Okay, understood, fine. Now what next? इसके आगे होना क्या है? इसके आगे होना क्या है? Now since this one is oxygen and this one is hydrogen, fine, this one is more electronegative, so always this is having a tendency to break this particular or pull the entire cloud of electron towards it, fine. So once this will come, where exactly this will go? This will come here, this will approach here, fine. If this will approach here, what will happen to this pi bond? This will definitely shift its location, right? Shifts its location, fine. So this has happened over here, fine. So in this very process, what will happen? This has to leave in the form of H plus. Once this bond was broken, there is no point in keeping the hydrogen here. No longer it will stay over here, right? So likewise, we can write here, if I just put a further arrow, right, I can put here like this, H plus, right? I can put like H plus. So what will happen to this? Once this has happened, what will happen to this? Okay, let me just write what will happen to this, fine. So now we have a R, we have a C. Now this has got converted to a double bond O. Yes or no? Double bond O, because this electron pair has already been given to form a pi bond, right? This pi bond was broken, fine, and this came over here, fine. So now what happened here? Now there is a formation of this, and now this has got a negative one, and we have got a W over here. Fine. Okay. Now what next? W over here. So we have still an anion, right? An extra charge on nitrogen, fine. This extra charge need to be converted to 1 because amide is CONH. So from where it will get the H plus? It will get the H plus from this, because the H plus was left out, right? Earlier it was left out from this, right? Now it is available. So what will have, and moreover we have introduced an ample amount of H2SO4 in the reaction media, fine. So that is why H plus, there is no deficiency of H plus as such, right? So what will happen here? Now once this is on, protonation will take place. Protonation of what? Protonation of this anionic nitrogen, fine. It is the protonation that eventually give rise to the formation of our compound of interest, that is your N substituted. Here the W corresponds to alkyl, aryl, heteroaryl, it's your choice, right? R also same thing, right? Because we started the reaction with ketoxime, and make sure that Beckmann rearrangement is basically, if I say Beckmann rearrangement reaction, right, it is basically involved in converting what? A ketoxime into a N substituted amide. N substituted amide is this. So this one is found to be the N substituted amide. So this is found to be the amide linkage, CONH, RCONH, and to that NH, one hydrogen, NH to one hydrogen is replaced with W, and W corresponds to alkyl. So this is how the entire reaction takes place actually. This is how the entire reaction takes place. Now, so this is all about the mechanism. It's very simple, right? Only thing is that you have to increase, or you have to use your wisdom, or rather you have to spend some quality time with this, right? So nothing supernatural is existing in this particular mechanism, right? So if you just sincerely approach to this particular reaction, to this particular mechanism, right, you can definitely get to know what is happening. So initially this amide, right, what happened? Protonation occurs. So protonation eventually leaves, make it more, a better leaving group, what we can say, right? So it can leave the compound at ease, right? So now once this has got protonated, so this has got the or it acquires the ability to leave the compound. So suddenly the group which was earlier in anti-relationship with the hydroxyl as well as this, right, it will definitely try to attack here. Fine. Once this will attack here, so then at ease it can release, it can leave the compound, right? So thus on removal of water it can acquire what? So this is found to be the 1, this one is 2, this one is 3, and this one is 4, and this one is 5, right? Chalo. So what happened here? So since it is W, actually W, fine. So what happened here? So this is now when once water, you know, left this particular compound, so what intermediate, so what happened to this? Again this got a positive charge, right? So once this got a positive, because W was already, you know, involved in making a bond with this to this, right? We have a positive charge over here. Now nucleophilic attack took place, right? It is the nucleophile, water is serving as the nucleophile. It is basically approached this carbon through its lone pair, right? And now the proton has to leave the intermediate. Why? Because after all, this pair of electrons will replenish the deficiency, right? That is why I have written here deprotonation, right? Deprotonation as well as nucleophilic attack, right? So now what happened? This has formed, right? After that, what will happen? Again this proton will try to leave, right? Once this will left, so deprotonation occurs here. It is the deprotonation that eventually leads to the formation of a keto moiety here. Now we have a nitrogen, on top of it we have a a charge, right? Now this charge will be used to protonate, right? This charge will be used to accept a proton, right? And finally we got the compound of interest, that is your amide, right? So this is all about the reaction mechanism, of your Beckmann rearrangement reaction. Let me just wrap up this with a simple example, right? The applications and all, or examples and all, right? Suppose ki you have started your reaction with, okay, let me just put one example. With that I can wrap up this one, right? Chalo. So now example is, suppose ki we have with us acetoxime, right? The starting material was found to be acetone as well as hydroxylamine, and when they came close together, when they united, right? So there is a formation of what? This oxime. So this is your acetoxime, because it was acetoxime. And I want to convert the acetoxime. So H2SO4 is found to be the reagent, because several times protonation, deprotonation is found to be an usual event over here, fine. So what will happen? H3C will remain same. Only thing is that the C double bond O and N is getting converted to NCH3, of course hydrogen, fine. So thus we got what? We got N-methyl. Then ethanamide. Why? 1, 2, this is 1, this is 2, 2 for eth, so this is ethanamide. So this is one example. Several examples are there, but the thing is that you make sure you do one thing. Let me do one thing. Let me just go back to the previous one. So if your job is to convert an oxime, okay, so this is the oxime, into an N-substituted amide in presence of this many acids as well as favorable conditions and all, right? You can just make what? You can just convert an oxime into an amide, right? So this is all about your Beckmann rearrangement reaction, right? So hope you understood, okay, the illustration of Beckmann rearrangement reaction. It's a simple, let me do one thing. Let me just project it, right, so that at least you can get to know about this. Fine, okay. Yeah. Now we can accommodate, fine. So this is all about the reactions and all, right? So I hope you understood. Now, as I said, always please put your comments, okay, in the comment box, so that at least we can grow. And let me just know that in the forthcoming sessions, right, which is the topic that you want me to deliver, right? So that is also an important thing, right? So thank you for your patience hearing. See you in my next video. Thank you.